Welcome everyone. Unfortunately, this is a re-record as the recording we made in class didn't have any audio with it. So this is a retry. Hopefully it'll go a little quicker since it's just me talking to an empty room. As you can see, we're going to talk about hyperbolic functions. Not a topic we see a whole lot of. For our potential engineers out there, particularly civil engineers, you're going to see more hyperbolic functions than other people. As you can see, I've kind of listed here the general properties of hyperbolic functions. They tend to be combinations of e to the x and e to the negative x, but they also have many properties of trig functions. And I'm going to show you here what I mean by those two connections. If you actually define hyperbolic sine and hyperbolic cosine, hyperbolic sine is e to the x minus e to the negative x over 2. Hyperbolic cosine is e to the x plus e to the negative x over 2. The other 4 trig functions also have different definitions, but we're actually not going to go into that much detail as you don't use those that frequently. What's interesting is you may be going, well, how could all those e's be connected to the hyperbolic functions? And this is one that I always get a little amused at. The paragraph at the beginning of this section in your book says that they are connected to each other through the use of complex numbers. Now, when I asked in class what a complex number was, I was disappointed to find out that I got 0 response. So as a reminder, complex numbers are those numbers outside the real numbers, such as 2 plus 3i, where they combine an imaginary number and a complex number together. Now, I personally have never ever seen complex numbers connected to the hyperbolic functions. I think it's way back deep in some pretty advanced mathematics. So as you can see, your book doesn't even go through and prove how these are connected. So unfortunately, you just have to trust the book and me on this one. Now, what am I going to ask you to do with the hyperbolic functions? And, right, well, at first, you're just going to be asked to evaluate some of them. And so if I ask you to evaluate, I may ask you to evaluate the hyperbolic sine of the natural log of 3. If you're going to do that, I simply want you to take natural log of 3 and put it into the equation for hyperbolic sine, which in this case would make it e to the natural log of 3 minus e to the negative natural log of 3 all over 2. And then you need to work that out. Now, in class today, they moaned and groaned when they saw the natural log, and then they realized that, no, this is a good thing. Since e and natural log of 3 are inverses and cancel each other out, you end up with just 3. Now, the question is, when you do e to the negative natural log of 3, does it still cancel? And the answer is no, it doesn't, because you can't have that negative there. So we needed to move the negative somewhere else, and in which case, if you realize it's really just negative 1, we can take it and move it back up here on the log, make that 3 to the negative 1 power, which is really nothing more than 1/3, and then divide it by 2. Now, doing a little mental arithmetic, because we don't need a calculator for this, 9/3 minus 1/3 would give us 8/3. And if you divide it by 2, that's the same thing as multiplying it by a half, and so we would get 4/3. And so our solution to that one would be 4/3. Now, you might be wondering, why does anybody care about hyperbolic functions? Well, hyperbolic cosine in particular is the most useful. And if you actually look at the graphs of the hyperbolic functions, you will find that the hyperbolic functions all have unique graphs of their own. I'm trying to get here so I can create a new tab and show you those hyperbolic functions. And in particular, the one we care about the most is hyperbolic cosine. And unfortunately, that didn't go to where I wanted it to. Well, that's kind of weird. It doesn't want to go find the hyperbolic graphs that I have bookmarked. Finally, okay, if we actually want to go look at our hyperbolic functions, unfortunately it's not letting me find them very well. Aha! Down here at the bottom we'll find the graphs of hyperbolic sine and cosine. The one in particular that we are really after is hyperbolic cosine. And you may say, but it's just a parabola. Well, no, it's not just a parabola. It is what we call a catenary. And to the people out in the engineering world, catenaries are incredibly useful. A catenary is structurally very, very sound. The St. Louis Arch is a catenary. You may think about some bridges you have seen that have curves like that, either underneath them as supports or above them, and you'll realize it's a catenary. Those all help make a structure be very sound, which is why the potential civil engineers out there may like catenaries. So technically, by definition, a catenary is nothing more than the shape you get if you take a string and pin it to something and you let it dangle naturally. That arch you get on a catenary, or that arch you get on the string, is a catenary. I'll spell that for you. So hyperbolic cosine is probably the most favorite of the hyperbolic functions. What I'm going to ask you to do through this assignment is simply do some calculus on them. Can you do derivatives of them? Can you integrate them? So we're going to look at a little bit of that. And the good news, there's good news and bad news. Their derivatives follow the derivatives we already know. You'll notice up here, hyperbolic sine, simply written with sine with an h behind it. Derivative of hyperbolic sine is hyperbolic cosine. However, the derivative of hyperbolic cosine is a positive hyperbolic sine. So it is one of those that changes. It's similar, but the sign changed. Now, there's only one other one that changes. So I'm going to challenge you to look here and see if you can find the other one that has changed its negative sign. Hyperbolic tangent, still secant squared. Hyperbolic cotangent is negative cosecant squared. That's normal. But hyperbolic secant is not normally a negative hyperbolic secant tangent. So that's the other one that is different that you'll have to look out for. Hyperbolic cosecant is still a negative cosecant cotangent. Now, the other thing I'm mentioning here that we're not going to particularly use a lot, but I want you to realize most of the trig identities, there are identities with hyperbolic functions, but our good friend sine squared equals cosine squared equals 1. In the land of hyperbolic functions, it's cosine squared minus sine squared equals 1. So they are similar but not the same. We could go through a massive list, and you may have noticed the website I was scrolling through had tons and tons of formulas and identities on it. What I want you to do is to simply do a few derivatives and integrations for me. Okay, so we're going to do just a quick derivative of a hyperbolic cosine of the square root of 1 minus x squared. This is back to the good old days, just basic derivatives with product, quotient, and chain rule. So hopefully, in this case, you're going up to hyperbolic cosine of square root of 1 minus x squared. So we're going to do a little chain rule here. All you have to know is what's the derivative of hyperbolic cosine. It is the one that's different. It's a hyperbolic sine. So then I will have that hyperbolic sine times the square root, or of the square root. But I need to do some chain rule. And since that square root is the same thing as this quantity up here to the 1/2 power, I'm simply going to put a 1/2 in front times 1 minus x squared to the negative 1/2 times the derivative of the inside of it, which would be negative 2x. Now, you are going to have to do a little bit of simplifying, but there's nothing very fancy here. The 2's would cancel, and they would drop the negative power back to the bottom. So you're going to end up with a square root quantity on the bottom. We're going to pull that x at the back clear up front and make that negative x times our hyperbolic sine of the square root of 1 minus x squared, and you've found a derivative. Nothing more than do a normal product, quotient, and chain rule. Just couple slight changes with our derivatives of these our hyperbolic trig functions. Okay, we're ready to try another one here. So this time we'll look at a hyperbolic cotangent of x times e to the hyperbolic cosecant x squared. And hopefully you're going, well, hey, that's two things multiplied. We need to do the product rule, which is simply nothing more than first, okay, derivative of the second, derivative of e is itself, but then we have to chain rule and do the derivative of that exponent. So derivative of hyperbolic cosecant is a negative cosecant of hyperbolic x squared cotangent of hyperbolic x squared. Be sure you keep x squared in both quantities. And then you have to do times the derivative inside of that, which would be 2x. Now, we've only gone halfway, though, so if we do the other half of our product rule, that was first d second, we also need to do plus second d first. So if I put the second in there times the derivative of the first, derivative of hyperbolic cotangent is a negative hyperbolic cosecant squared, and that would end it. We aren't going to bother to simplify one like that. We'll leave it that way. So basically this is going to be good practice on your original derivatives with product, quotient, and chain rule. You're also going to be asked to do a couple integrations, and when you integrate, it's not probably going to be simple ones. You're probably looking at some u substitutions. In this case, since you see you got hyperbolic sine to the 7th power, we're going, well, okay, can't have a 7th power, so I'm going to have to u substitute that hyperbolic sine, which is going to give me u to the 7th times the hyperbolic cosine. We're going to hope that cancels in a minute once we do find out what dx is equal to. So if I do our derivative here, derivative of sine is cosine, and then when I divide that over, I would have du over hyperbolic cosine. And once I substitute that in there, it beautifully cancels. And I only have to integrate u to the 7th, which will be 1/8 u to the 8th. Don't forget your plus c. And then finally put your substitution back in, so we actually have 1/8 times the hyperbolic sine to the 8th power of x plus c. Once again, good practice on your basic skills. I do have one slightly tricky one I want to pull off here. We didn't do this one in class. This is an extra, but since I have time, I want to add this. If you do the integration of a hyperbolic cotangent, there isn't one. I can't use substitute because there's nothing to cancel with. So you have to get a touch sneaky with this one and go, oh, I could change cotangent into, yes, you said it, cosine over sine. Once I put it into cosine over sine, then I can try to use substitute it. The question is, which one do I substitute for, the cosine or the sine? Well, the bottom of a fraction is always more trouble. So we're going to substitute the hyperbolic sine out. Its derivative is going to be hyperbolic cosine. So when I put the dx in there, you can see that the hyperbolic cosine cancels, and I'm left with 1 over u. Now, this is where I'm a little concerned because it's been a little bit, but how do you integrate 1 over u? Should I bring it up? Obviously, over here to the left, I've got it crossed out, so it must not be right. But can I do u to the -1? And hopefully you're screaming, no! Integration of 1 over u is natural log of u. So I did my natural log. Don't forget your absolute value. Substituted my u back in as hyperbolic sine, and ended up, of course, with a plus c on it. So that takes care of that one. So you can occasionally do some minor little fancy work with some identities. You do have a couple problems at the end where I'm going to ask you to find some area or volumes. Okay, I know you don't know these graphs. If you look on page 498, as you'll notice I have it written here, you'll find the graphs of them. In this case, I wanted the area enclosed by hyperbolic cosine, y equals 1, and a vertical line at natural log of 4. Okay, they're going to be really simple. If I ask you to do area, then you simply need to do the integration of top minus bottom. So top minus bottom was cosine minus 1. and then we integrated from 0 to natural log of 4. Use your calculators to do this integration, and you'll also discover I've put a hint over here about where to find them in your calculator. Good luck. Have a great spring break.